Dr. R. Sugurat Samuel is working as professor in physics in SRM University, Chennai. He is also training students for IIT JEE, AIEEE, and BITSAT. He has more than 16 years of academic experience both in teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals. It is prescribed book in the syllabus for BSc Electronic Science by University of Madras. He has attended and presented papers in several national and international conferences and conducted many training programs and workshops. He has experience in both regular classroom teaching and also online teaching. His research areas are ultrasonics, polymers, crystal growth, and photovoltaic systems.
Welcome to UGC lecture series on Applied Sciences Electronics. We have been listening to a series of lectures on the subject Electricity and Basic Electronics for the BSc Electronic Sciences degree program. This subject is the first paper in the first semester. This lecture is the 52nd lecture in the series. We have started in the last lecture the concepts of digital electronics. In continuation to that, in today's lecture, we are going to learn about the logical operations that are possible. In the last lecture, towards the end of the lecture, I have given what are the logical expressions possible or the logical operations possible with the digital world. In continuation to that, in today's lecture, we are going to see some of the logical operations that are related to our curriculum. Before we start the lecture, let us see the session outline of today's lecture. In this session, we are going to see the introduction to digital electronics, the logical expressions, Boolean algebra, the logic gates namely OR, AND and NOT, and again the combinational gates called NOR gate and NAND gate. So let us start our discussion with the logical expression. What is a logical expression? It is an expression which involves the logical operators. The logical operators, I have given a brief of it in the last lecture. So those logical operators will be found in the logical expression. There will be a definite output for each operator, logical operator, and the expression would also have a logical output. That logical output would be either true or false, or in terms of voltage high or low, or in terms of number 0 or 1, like that. So the possible output of a logical expression is a logical value, that is true or false. So let us see what does that mean. Logical operations, an operation that acts on binary numbers to produce a result according to the laws of Boolean logic, is called the logical operation. Boolean logic is a form of algebra in which all values are reduced to either true or false. So the output of a logical expression is only 2, either true or false. That will be the output of a logical expressions. Let's see what does that mean further. In Boolean algebra, the distinguishing factor of the algebra, which is a division in mathematics that deals only with the study of binary variables or logical variables. We have two types of logic, namely positive logic and negative logic. What is the meaning of the positive and negative logic? I said already, in the case of a expression, logical expression, the output or the end result would be a logical value, which is 0 or 1, true or false, like that. Now, as far as the value is concerned, we can operate the high and low value in the positive side or on the negative side also. But the only thing is the high and low should be there. If we operate between 0 and a positive value, then it is called a positive logic. The high value, the positive value is the high value, 0 would be lower than that, so it is a lower value, high and low. Similarly, we can fix the extremes, high and low, between 0 and negative also. That is called a negative logic. In that case, the 0 will become high and any negative value will become low. So, it is not that we are supposed to act between a high value, which is a positive value, 0 is a low value. There is no such restriction. We can operate the system between 0 and a negative value also. The negative value automatically takes the lower value, lower state. So, that is what is called the negative logic and the positive logic. So, let us see what it is further. Both the positive and negative logic again deal with the binary systems, but the following way. In the case of positive logic, the true is 1 and the false is 0. And in the case of negative logic, just it is reversed. True means it is 0 and the false means it is 1. Because we know the meaning, we can operate between the other two manner also. And one more explanation is, as I have stated, in the case of voltages, between 0 and a positive value it is called positive. Between a negative value and 0, if it is operated, it is called a negative logic. Just it is reversed. That is the difference between positive and negative logic. But for our discussions, we will restrict ourselves with the positive logic only. Now, let us see what is the meaning of gate, the logic gates, because in our curriculum, some of the logic gates are mentioned. So, we need to strengthen our understanding on the Boolean algebra and the binary system before we learn about the logic gates. So, let us see what is a gate. A logic gate is an elementary building block of a digital circuit. Most logic gates or circuits have two inputs and one output. At any given moment, every terminal is in one of the two binary conditions, low, which is 0, or high, which is 1, represented by different voltage levels. The key factor of the logic gate is the output is just 1. We can have any number of inputs, at least 2 input for some of the gates. We have a gate which has only one input also and one output, but invariably all the gates will have an output as one terminal, one output. That would be a logical output. What is the meaning of logical output? The output should be either high or low, or in terms of logical variable, when we want to specify, it is true or false. So, a logic gate is the one which operates on the logical operators. Actually, the logic gates are circuits, electronic circuits, which would produce one output based on the operator. So, that is the meaning of logic gate. Now, what are the operators possible, or what are the logical operators we have? Let us see what the operators and the related gates also. The basic logic gates are these. The basic elements that make up a digital system are OR, AND and NOT gates. The gates are normally represented with the uppercase here. So, OR is one logical operator, AND is one logical operator, NOT is one logical operator. The circuits which produce these operations are called the gates. So, these are the main 3 gates. These 3 gates are called the basic gates. All the possible inputs and outputs of a logic circuit are represented in a table called truth table. So, the truth table would contain the possible combinations of the inputs and also the output of that particular gate. So, that is called the truth table. When we have a look at the truth table, we actually get the output of the gate for whatever combination of input that we decide to give. So, that is the truth table. It will have the numbers zeros and ones in combinations. Let us see what are the basic gates possible. We will learn about each gate from the 3 gates one by one. Let us see what is the first gate we are going to see. It is an OR gate. An OR gate has 2 or more inputs but only one output. It is known as OR gate because the output is high if any one or all the inputs are high. The Boolean expression to represent the OR gate is given by this expression: y is equal to a plus b. The plus symbol here we use is the symbol used for this OR operation. Here I would like to give an additional information. The symbols that we use for representing the logical operators have a different meaning. Actually, when we use the plus sign, it is used for addition, any number. Say 3 plus 4 is equal to 7. We say there the plus sign is used. There the operation performed by the plus symbol is a different operation, it adds. But in the case of a Boolean expression, the plus symbol that we use has entirely a different meaning. It is the OR operation. So, we need to even read the a plus b here as a or b. That is how we need to read, because the plus represents the OR operation, a or b. What is the OR operation? It clearly says the output is 1 if any one or more than one inputs is high. So, which includes all the possible input combinations. As far as a 2 terminal input is concerned, namely A and B, we have 4 such combinations. Both A and B could be low. Either A as a low value and B as a high value, then A as a high value, B as a low value, and then both A and B as high values. So, there are 4 combinations. For these 4 combinations, what would be the output? So, let us have a look at the truth table. The truth table gives us an idea about the output. So, before we do so, let us have a short break. Welcome back. We are looking at the OR operation. We need to have a look at the truth table, which gives the output of the different combinational inputs. So, let us have a look at the truth table of OR gate. So, this is how the truth table looks like. We have 2 inputs A and B. As I said, there are 4 combinational inputs: 0 0, 0 1, 1 0 and 1 1 for the A and B inputs, and the output is represented as y, which is equal to A or B. And in the case of first combination, both A and B are 0, low, so the output is also low. After that, at least any one input is a high value, so the output is high. That is a typical meaning of OR operation. This is the circuit symbol used for OR gate. There are 2 inputs. So, a OR gate should at least have 2 inputs. We have more than 2 inputs also possible for an OR gate. So, Here the basic OR gate is taken with a 2 input gate and there is one output, and this OR gate could be represented as an electronic circuit because either A or B should be high to get an output high, either A or B or both high to get an output high. How this is represented? With an electrical circuit with the switches, typical switches connected. Let's have an equivalent OR operation using an electrical circuit. Let's have a look at the circuit. Here a typical switch is connected, there is a power supply. To get an output as a high value, what does it mean here? The current should flow through the output, the lamp. If current flows through the lamp, the current will glow, then it represents the on condition or the high condition. If the current is not there, then the lamp cannot glow, which represents the off state or the low state. If both A and B are open, that is what is represented here as 0, 0. If both A and B are open, there is no current possible in the circuit, the output is low. Either A or B or both A and B are closed, then there will be definitely a current possible in the output, which is the lamp will glow, so which is the high condition. So at least one input is to be closed or both the inputs should be closed, or that is the meaning of 1 here to get an output 1. So the OR operation is easily understood using 2 switches connected in parallel. If any one switch is closed, it is sufficient to get an output. If both are closed also, we get a output because the current is allowed to flow through the lamp. This is OR operation. Now at this point I would like to stop before we go to the next gate. If suppose we have 3 inputs for an OR gate, A, B and C, and when we have the possibilities to give zeros and ones to these terminals in a systematic way, how many combinational inputs are possible, like A0, B0, C0, A0, B0, C1, like that. If we keep on varying the inputs, how many such combinational inputs we could give? By the permutation, when we write it, it is 2 to the power 3. There are 2 variables possible, 0 and 1 for the 3 terminals A, B, C. So it is 2 to the power 3, which is 8. So 8 combinational inputs we could give for a 3 terminal OR gate. We can even design one 3 terminal OR gate, but right now let us go ahead with the other logic gate, which does one more logical operation, that is AND gate. What is the meaning of AND operation and what is the electric circuit explanation for AND gate? Let us see now. An AND gate has 2 or more inputs but only one output. It is known as AND gate because the output is high only when all the inputs are high. The Boolean expression to represent AND gate is given by this expression, y is equal to A dot B. Here the dot should be read as AND. So we should read it as A and B. Y is equal to A and B. As I said, the period, the dot symbol we use here has a meaning. That meaning is the logical operation AND. What is A and B? As per the explanation we have got, to get an output high, both A and B input should be high. That is the condition. So that is why the name is also called AND operation. Both A and B should be high to give an output high. What about the other combinations? Obviously the output will be 0 for all other combinations. So let us have a look at the truth table to have an understanding of the AND operation. In the case of AND operation, again 2 inputs are taken, A and B. See, when we look at the output is 1 only both A and B are 1. That means A should be high, B should be high to get an output high. For all other combinations, any 1 is 0, so the output is not high. That is the meaning. Only for the last combinational input, in which both the inputs are 1, no, the output is 1. This is the circuit symbol for the AND gate. When we compare this symbol with the OR gate, no, there is a difference. Here there is a straight line, but in the previous case, no, for OR gate, this part was slightly curved. So let's have a look at the OR gate, how the two gates are different in symbols. See, in the case of OR gate, it is curved, and in the case of AND gate, it is straightened, and the output is A and B. What is the circuit equivalent? In the case of previous logical operation, or we used two switches in parallel connection. How the two switches are to be connected to act as a AND gate? Here it should be connected in series, because both the switches should be closed to allow the current to flow through. Both should be on to get an on as the output state. So let's have a look at the circuit. The two switches are connected in series. A is connected and B is connected here in series. Then only the current will flow, the output is on. Even if any one is off, no, the off here is 0, the output will be 0. So it is typically explaining the AND gate operation. Now again, for the AND gate also, we can have many more inputs. We need not restrict with only 2 inputs, but at least we need to give 2 inputs for AND gate. But we can have more than 2 also. Accordingly, the output will be considered when all the inputs are high, then only the output is high. For all other combinational inputs, the output will be 0. So that's what we have to keep in mind as far as the AND gate is concerned. Now, one more gate we need to learn, which has only one input and we have one output. All the gates will have only one output, which is the same thing for all the gates, but inputs could be any number based on the operation. But for this gate, only one input and only one output, that is called the NOT gate, N-O-T, NOT gate. Let's see what it is. The NOT gate is a gate with only one input and one output. It is so called because the output is the complement to the input, or we can call that as the output is not the input. That's why it's called the NOT gate. It is also known as an inverter. The Boolean expression to represent the NOT operation is y is equal to a with a bar. Here the bar is a complement. It is read as a complement. Normally we call it as a bar, but the typical way we read it, it is a complement, b complement, like that. But here we have only one input, so it's called a complement. What is a? Which is the complement of the a without a bar on the top. If we take a complement 2 times, a's complement when we take, it is actually a. So that is the meaning of the complement here. A is not the output, so it's called the NOT gate. How the truth table appears for NOT gate? It's very simple, because there is only one input and one output. The output is not the input. So let's have a look at the truth table. See here, there is only one input. The output is not the input. When we have 0 as the input, the output is 1, which is not 0. And 1 as the input, 0 is the output. This 0 is not the 1. So that's why it's called NOT gate. This is how the NOT gate is represented in a circuit with one input. We have a triangle followed by a small circle. The circle normally is used to take the complement. So the output is the a complement. Again, we can discuss about the circuit equivalent for the NOT operation. When we represent the circuits with switches, only one switch is required because only one input is possible for a NOT gate. How the switch is connected? It's quite interesting. Let's see the circuit connection. When we on the switch, the current should be 0 on the lamp, and when we off the switch off the circuit, the switch is off, the current should flow through the lamp. So, how it is done here? Let's have a look at the diagram. We have a voltage source which supplies the current through the entire circuit. When we connect the switch in parallel to the lamp, when the switch is open, when we don't connect the switch, when the switch is open, the current is supplied, the current flows through the lamp and the lamp glows. So, even when the switch is in the off state, the output is in the on state because the current flows through the bulb. When we switch on the switch, when we connect the switch, when it bring it to the on condition, the entire current is likely to flow through the switch only. The current will not flow through the lamp, which offers some resistance. So, no current flows through the lamp, current takes the easy path and the current does not flow, so it's off. The lamp will not glow, so it is in the off state. When the switch is in the on state, the bulb is in the off state. So, which is easily explaining the NOT operation here. So, we have equipped ourselves with the basic logical operators, namely the OR operator, AND operator, and also the NOT operator. These are the circuits which do the operations. They are called the gates. So, each gate we have seen: OR gate, AND gate, and NOT gate. Typically, we need to learn about the circuits. What are the electronic components we use in designing the gates? We will learn about all that in the future lectures. I have mentioned in the beginning, we have some combinational gates possible. Let's have a look at the combinational gates. When we combine any two of these gates together, we will have a combinational gates. Normally, we will connect a NOT gate to the output of either the OR gate or the AND gate. So, when we connect a NOT gate to the output of, say for example, an OR gate, we will get a NOR gate. And similarly, when we connect the NOT gate to the output of an AND gate, we will get a NAND gate. So, we will reserve the concepts of the combinational gates for the upcoming lectures. So, with this, I would like to conclude today's lecture. Before we conclude this lecture, let's have a look at the session summary. In this session, we have seen the introduction to the digital electronics by way of learning logical expressions, Boolean algebra, logic gates, the basic logic gates, namely OR, AND, and NOT gate. The combinational gates I would like to reserve for the future lectures. Now, let's test our understanding by answering these questions. What is a logical expression? Define Boolean algebra. Explain the basic logic gates with their truth tables. We will learn about the combinational gates and the typical circuits, the circuit components used for designing the three gates we learned today, namely OR, AND, and NOT, in the upcoming lectures. All the best and thank you for listening.